The basic conditions for plastic analysis are as follows. Firstly, a mechanism must form. That is, a sufficient number of plastic hinges need to form to create a state of plastic collapse. Secondly, equilibrium, where the bending moment diagram must be in equilibrium with the applied loads. Thirdly, the yield condition. That is, the plastic moment cannot be exceeded anywhere in the collapse mechanism. Where the plastic moment is exceeded, we say that a yield violation results. The concept of statical indeterminacy. Structures are often statically indeterminate. As a result, more than one hinge is required for collapse. For statically determinate structures, only one hinge is required to form a mechanism. For example, a simply supported beam. A mechanism can be formed by either removing one of the supports or introducing a hinge somewhere along the midspan of the structure. For statically indeterminate structures, more than one hinge is required. For a built-in beam, in order for a collapse mechanism to form, we either remove one of the end supports and introduce a release at the remaining end, or we introduce a sufficient number of hinges to form a collapse mechanism. In this case, it's 3 hinges. The degree of statical indeterminacy can be formally determined by using the following formula. We say that the degree of statical indeterminacy is given by alpha, and this is equal to n times by m minus j plus r minus p, where n is the number of members in the structure, j is the number of joints, r is the number of reactions, and p the number of pins. The value n is equal to 3 for plane frames or portal frames, and n is equal to 2 for beams. To show you how this formula is used, consider the following portal frame. This frame is fixed at its base with some loading. Firstly, the number of members in the system. We have 1, 2, and 3. The number of joints, 1, 2, 3, and 4. And finally, the number of reactions. We have the vertical reactions, the horizontal reactions, and the moment reactions. And there are 3 at each support because this is fixed at its base. So as a result, the number of reactions for this structure equals 6. To summarize, M is equal to 3, J is equal to 4, R is equal to 6. There are no pins in this structure, so P is equal to 0. And because this is a plane frame, N is equal to 3. Therefore, alpha is equal to 3 times 3 minus 4 plus 6, which is equal to 3. For a complete collapse mechanism then, we must have alpha plus 1 equal to 4 hinges. The next important concept in plastic analysis is that of critical sections. Critical sections are where plastic hinges can potentially form and occur in the following locations. If we consider a general portal frame, with a concentrated load and a distributed load, plastic hinges can form firstly at fixed supports, secondly under concentrated loads, thirdly at joints, and finally somewhere underneath the distributed load. The exact position of the hinge under the distributed load will depend upon the bending moment distribution of the whole structure. The final place to be aware of a plastic hinge formation is at a change in cross-section. For example, with this cantilever, we have one section which has a plastic moment capacity of 2 MP, and another section which has a capacity of MP. Then the plastic hinge will form at the interface of these two sections. There are two main approaches to plastic analysis. Firstly, the static approach, and secondly, the kinematic approach. In the static approach, plastic hinges first form at the most highly stressed location. Based upon knowledge of the elastic bending moment distribution, we can determine the location of these most highly stressed sections and then conduct our plastic analysis. For an example, consider the following simply supported beam. This has a concentrated load at the middle, scaled by a plastic collapse load factor, lambda, times by W, and a cross-section property of MP. The load is located at the center of the beam, and the objective is to find the collapse load factor on W. The elastic bending moment distribution is given as follows, and this has a peak value of M equal to the collapse load factor times by WL over 4 as determined by statics. A plastic collapse, a plastic hinge forms in the center of the beam, and at this plastic hinge there is a moment of M plastic because we are arguing the whole cross-section has fully yielded. We can then say that the value of MP is equal to lambda c times by WL over 4, and consequently the plastic collapse load factor is equal to 4 times by MP over WL. The idea behind the plastic collapse load factor is to determine the extent to which we can scale up any given applied load to achieve full plastic capacity of the cross-section. The value of MP is sometimes referred to as the design moment, and the collapse load factor is sometimes just used in analysis. For statically indeterminate structures, a similar process is followed. This time, consider the built-in beam. With a uniformly distributed load of W. The equilibrium state is given by the elastic bending moment distribution, which in this case looks like this, with n moments MA and MB, and a central moment of MC. The maximum overall value of bending moment for this distribution is given by WL squared over 8 under the conditions of yield. We can argue that the positive and negative bending moments cannot exceed the plastic collapse moment. And finally, the resulting mechanism has 3 plastic hinges, all with value MP. We note then that MA has to equal minus MP and MB has to equal MP. For MC, we say that that is equal to WL squared over 8 plus the contributions of the support moments or reaction moments, MA plus MB over 2. And this all has to equal MP. Upon substituting the values for MA and MB into this expression, we get WL squared over 8 equal to 2 times MP. So the collapse load, WC, is equal to 16 times MP over L squared.